So I'm going to talk about polynomials. Now, there are some characteristics about polynomials that you need to know. They are smooth functions. There's no points. What I mean by that is like a smooth function is like something you could do like on a roller coaster. There's no points. So in other words, you wouldn't see something like that where there's this jagged edge. Okay, there's no harsh line drop off where you get this like looks like it's broken kind of thing. And also, besides it's being smooth, its domain is all real numbers. And this is a big one. Okay, so in order for things to have domain being all real numbers, our exponents need to be nice. And what I mean by that is integer values such as 3 and 1. So this is a polynomial. Now, there's this term called degree, and you can have the degree of the whole polynomial, and you can also have a degree of a term. So the degree of this term is 3. The degree of this term is 1. The degree of this term here, remember x got moved up, or I'm saying, look, it's 1 over x, and it's x to the 1. But if I write it here, it moves up. Oh, I said integer. I was incorrect on that. Whole number, forgive me. It has to be a positive. Cannot be negative. And the reason it can't be negative is it puts this x down into the denominator, and because it's in the denominator, 0 is not a value, and that violates the idea of the domain being all real numbers. So the degree of this term is 1. I'm going to write this term really all crazy. So this will be x, y, z, and then it'll be x squared y to the 4th, and then this will be x to the 10th. Okay, so the degree of this term would be 3, because there's a 1, there's a 1, there's a 1. 1 plus 1 plus 1. The degree of this term would be 6. The degree of this term would be 10. So the degree of this entire function, if it was a function, would be 10. So the degree of the polynomial is the degree of the term that has the highest degree. And what that degree means is that if you have a degree of 3, you have 3 roots. Now sometimes they're double roots, and those have like unusual characteristics, and we have to talk about that at another point in time. But basically, and I do say basically, when you have 3 roots, it means there are 3 places that cross the x-axis. Now we have to be careful because we have to consider the fact that there's the potential of complex roots. So sometimes you get complex roots, and I'll just make this comment that if you get a complex root, you'll always get a second complex root. They always come in pairs. Okay. The other thing is that you get this thing called multiplicity. And we'll talk about multiplicity in a second. But if you have an even multiplicity at a root, what ends up happening is the graph just touches and comes back the way it came. And if you have an odd multiplicity at that root, and a root is where the graph crosses the x-axis, you get something that looks like this, where it travels through. Now, you could have it doing that on an even root, and you could have it doing that on an odd root, but I didn't want to confuse the functions too much. All right, so polynomial, yes, degree 3. The degree of that term is 3, the degree of that term is 1. Polynomial, no, because the degree, or the exponent here is a -1. Is this a polynomial? The answer is yes, and the degree is 3. Now, the degree of that term is 3, the degree of that term is 2, the degree of that term is 1, the degree of that term is 0. And we take the degree of the highest, the degree of the term that has the highest degree, so the degree is 3. Okay, I have 5x to the 1/2 plus 3x squared. No, it's not a polynomial. It's x to the 1/2. And 1/2, if you can recall, is really the square root of x to the first power. Now, let me just talk about that for a minute. So if you have x to the 3/4, that's the 4th root of x cubed. And so when we start dealing with like things that can't have certain numbers plugged in, we violate the idea of the domain being all real numbers. And so if you see this in a polynomial or if you see this in a function, it's not a polynomial. If you see this in a function, it's not a polynomial. If you see this in a function, not a polynomial. So just to go farther, so x to the 7/10 was the 10th root of x to the 7th. X to the pi, well, you have to remember that pi is an irrational number. So you have a whole number part, you have the 3, and then it's multiplied by x to the 0.14159, which is all the decimal. And this part is irrational. It never repeats. Can't make a fraction out of it. And so we really don't deal with it well. Okay, so you're going to have, you get something like this. It's not a polynomial. Okay. Now you'll notice I do have pi up here. Pi is the coefficient. We can multiply by pi. We can subtract pi x. It just looks a little strange. Okay. Now, I'm going to take, and one of the things it's going to ask you is translations again. So sorry about the moving video. So we're going to work off the base function x to the 4th. Well, if our base function is x to the 4th, and that's what the base function would look like. Here's our x-axis, here's our y-axis. What if you take f of x is equal to x plus 1 all raised to the 4th? Well, what's going to happen is that plus 1, because it's in the argument, is going to shift our graph 1 unit to the left. Okay. What happens if we're dealing with something that looks like this? So we have f of x is equal to 1/2 the quantity x minus 1 raised to the 5th power minus 2. Well, the minus 2, because it's just being added on to the base function or subtracted off of the base function, is a vertical shift. And since it's negative, it's down 2 units. And this is in the argument. Okay, the base function's x to the 5th. So this is minus 1 in the argument, so it's going to move it right 1 unit. And this 1/2 is a vertical compression. The reason it's a vertical compression is because it's less than 1. It's between 0 and 1, in fact. And if it was negative, it'd flip the graph over. Okay, so 2 problems I'm going to do real quickly. Number 41, it says the real zeros are -1, 1, and 3. Well, these are roots, and it says the degree is 3. Okay, so we have a degree being 3, and we have 3 roots, so that matches up. And the way you deal with the roots is you come and you bring them into your function as opposites. So remember, it's the reverse of the zero product property. I say remember. That's an inappropriate statement, or incorrect statement. We have to think about it like it's the zero product property. So this is x plus 1 for that one. This is x minus 1, and this is x minus 3. And then we FOIL it out. We take 2 at a time. So I'm going to do these 2 first, and I'm going to get x squared minus 1 times the quantity x minus 3. And then we FOIL these out, and we end up with x cubed minus 3x squared minus x plus 3. And you'll notice that that 3 matches that 3. Now I did number 48, and I've got about a minute and a half left before I've got to stop, so this is going to be a rush. So -2 has multiplicity 2. Well, what that means is -2 comes in as x plus 2, but then multiplicity of 2 means it's going to be squared. And then the root is 4 with multiplicity 1, so I write x minus 4. It comes in as the opposite, and then I have it to the 1st power. Well, x plus 2 times x plus 2 times x minus 4. Well, I FOIL those, and I get x squared plus 4x plus 4 times x minus 4. Now I went ahead and did all the multiplication, and I combined like terms, and I ended up with x cubed minus 12x minus 16. That 3 is because we have a degree of 3, and we have multiplicity 2 plus 1. All right, that's it for that bit. Talk to you.